Okay, here we go. We're rolling. This is a new way of recording videos for me, so we'll see how this goes. Um, Today we're going to talk about heaps and building them quickly. So if we wanted to build a heap and we wanted to do it quickly, where the input to our algorithm was an unordered array, and what we wanted out of the algorithm was a heap ordered array, what algorithm should we use to do that? The naive approach to do this would cost n log n, and this is pretty obvious. The algorithm would be to insert each of the n items that we have in our array one by one, and each of those inserts costs up to log n time. Since there are n of them, n log n. But there's an elegant algorithm that we're going to talk about today that can make it go much faster. By the way, you may hear bird songs, a lot of rain, traffic noises. It's all part of the magic of today's lecture. So I hope you enjoy that too. What we're talking about today is called the build-heap or make-heap algorithms. Just the name differs depending on the context, but it's the same thing. And what it can do is build a heap in order n time. And the algorithm itself is actually ridiculously simple, as long as we have bubble down already written. And the analysis is not so simple, but we'll go over that as well. So here's the way it works. We're going to start at the second lowest level of our heap. So the lowest level of our heap, all these down here, we can consider each of these to be already in heap order. Now let me explain what I mean by that. If you consider 26 by itself, just by itself, it is a heap, right? It's a min-ordered heap by itself, and it's already in order. So is 8, so is 28, 4, and so on. All of these by themselves are miniature heaps that are in order. So we're going to skip this lowest level, and we'll move up to the next lowest level, just above the leaves. And we'll start, say, at 21. We'll start at the right end of this heap. Now, by the way, let me back up for just a second here. Let's imagine that this is the structure that we're working with. It has this structure as a tree-based heap. But let's also imagine that we're actually implementing this with an array. So while we're picturing this as a tree, it's actually stored in an array. If we start at 21 and we consider what are its children, it has a child of 10 and a child of 31, and clearly it's not in heap order with respect to its children. But both of its children are miniature heaps that are in order. So if we just bubble down at 21 right here and swap it with 10, we'll get something that the entirety of this heap rooted at 21, or would be rooted at 10, is now in heap order. And we can do the same thing here and here and here. So that's what this first statement says. Start at the second lowest level of the heap, and then we're going to bubble down each node at that level, starting from the right and moving left, so that this forms a heap, and this forms a heap, and the heap rooted here is a heap, and so on. Then we're going to, once we've done that, this is a heap, this is a heap, this is a heap, this is a heap. Then we're going to move up one level and bubble down at that level, and then that one, and then this is a heap, and then this will be a heap, and then we're going to move up to the root, and then we're done. So we bubble down at the root, and then we're done. So we start at the bottom, second lowest level of the heap, we bubble down everything there, then we move up one level, bubble down everything there, and we keep going until we reach the root. Okay, so let's do this example that I've already sketched out here. So the array that I've highlighted in the text here is exactly the same as this tree structure that we're picturing right here. Okay, I've just laid it out as a tree, but we would actually implement this in an array. Okay, so let's do this algorithm. We start here at the second lowest level of the heap, and we're going to swap 21 and 10. Okay, then we'll move to this heap, and we'll swap 20, we'll bubble down at 26, which is going to result in swapping 22 and 26. And here, 13 and 4 will swap, because we're bubbling down at 13. Okay, and then 27 is going to be bubbled down to where 8 is. Okay. Now we've done everything at this level, and notice that 10 is the root of a new heap, 22 is the root of a heap, 4 and 8 are the roots of each of these little miniature heaps. So we'll move up to this level. Now we're here. And when we're here, we bubble down at 4, and 4 is already in heap order with respect to all of its children, so we don't have to do anything. But we would call bubble down on 4, and essentially it would do nothing. We move over here to 30. We bubble down at 30, and what happens? Well, it's going to compare with the least of its two children, 4 and 8, so we'll swap with 4. So 30 moves down, 4 moves up. Now, we're going to continue bubbling down at 30, and 30 compared to the lesser of its two children, which is 13, so we'll swap 13 and 30. Okay, so now 30's reached the bottom of the heap, and we're done with that bubble down that started up here. Finally, we're going to move up one level to the root, and we'll compare it with the lesser of its two children. It has equal children, so we could take either one. We need some tiebreaker. Let's say that we take the right side. It doesn't actually matter that much for this example. And so we'll swap 19 with 4 and continue our bubble down. Continue it here. Swap 19 with the lesser of its two children, which is 10. Okay, and then we would end here because 19 is in heap order with respect to its children. So that's our example, and you can sort of see how this works because we're just building little heaps and then bigger heaps and then bigger heaps until we get to the root. All right, so the analysis of this algorithm, like I said, is a little bit subtle, let's say. Okay, at first glance, this appears to be an n log n algorithm. Why does it appear to be an n log n algorithm? Well, if you consider how many nodes are there at the bottom of this heap, well, there are roughly n over 2 nodes at the bottom of this heap. Roughly half of a heap is down at the leaves. And then if you move up one level, there are half as many of those. So there's roughly n over 4 there, and there's roughly n over 8 here, and n over 16 here, and so on. Okay, and as you go up, this divides by 2 each time, right? So it appears that we're doing bubble down on roughly half. We're calling bubble down on roughly half of all of the nodes, if you sum those up. So it sounds like it should be log n for bubble down times n over 2, which is n log n, but it's actually not if we do the correct analysis. So the reason for this is that the bubble down, as we think of it, if you start from the root, it costs log n, but if you're starting from way down here, it only costs 1 unit of time to compare it to its children and possibly bubble down 1, because the furthest you can go from here is 1 level. Okay, and from this next level up, the furthest you can go is 2 levels down. And it's only once you get way up into the top of the heap that you could possibly go log n levels. And there are very few of those, and there are very many of these. There are lots of these bubble down calls, which are very cheap. There are very few of these expensive ones. Okay, so that's what we're saying here. So let's explain a little bit more carefully why this is. Okay, this is what I just talked about, right? At the lowest level, we have n over 2 items. The next lowest level, we have n over 4 items, which require 1 step to get bubbled down at most. Next is n over 8. And then we can generalize this, that at the ith level from the bottom of the heap, it has n divided by 2 to the I plus 1 items, which may be bubbled down I steps. Okay? So let's think about this as a summation of all the work that we have to do. This is going to be n divided by 4. Let me erase this and show you the work here. This is n divided by 4 times 1. Well, what's that n over 4? That's the number of items at the second lowest level of the heap. And what's the times 1? That's the number of levels that they could possibly go down. And then there are n over 8 items that could be bubbled down 2 levels. And then there are n over 16 items that could be bubbled down 3 levels, and so on. There's an ellipsis here because we're going to keep going all the way up to the root of the heap. Okay, we could rewrite this as n times 1 divided by 2 squared plus n times 2 divided by 2 cubed plus n times 3 divided by 2 to the fourth. So this is just a rewriting of this equation up here. Okay, now we'll rewrite this as a summation. So we'll rewrite this as a summation for I equals 1 up to log base 2 of n of those terms. We have I times n divided by 2 to the I plus 1. Okay, that's the summation. That's just a summation notation of what we were just dealing with. So that's from the second lowest level up to the top of the heap. Let me move this a little bit, get a better focus. This is just a summation notation of what we just had. Okay. Now, what we can do is we can pull out this n because it doesn't depend on the loop. So we'll pull out n. We can also pull out a factor of 2. In other words, this 2 to the I plus 1, that plus 1 is a little bit annoying. So we'll pull out a factor of 2. And this is just this a little bit simpler sum, n over 2 of I equals 1 up to log n of I divided by 2 to the I. Okay. Now, what is this? So we know what n over 2 is. That's easy. But what is this I summation of I divided by 2 to the I? Well, we don't know. And we're not going to calculate this exactly. What we're going to do is we're going to put a bound on this that is easier to calculate a little bit. And let's look at the first few terms of this. The first few terms of this sum are 1 over 2 plus 2 over 4. Well, you know that that is 1 plus 3 over 8 plus 4 over 16 plus ... Okay, and this is going to go up to log n over 2 to the log n. What do we know about these terms? Well, one thing that we notice is that the numerator is growing linearly and the denominator is growing exponentially. So that means that these terms are very quickly going, these individual terms are very quickly going to 0. So this summation is going to converge on a particular value. And what is that value? Well, again, we don't know. But I guarantee you that this summation is going to be less than this summation. Let's rewrite this. N over 2, the sum I equals 1 up to infinity. What? Infinity, yes, of I over 2 to the I. Now, you would agree with me that this is less than this because there are more terms over here. And the reason we're using infinity here instead of this is so that we can just compute the convergence of this sum. And we're not going to compute it directly. I'm just going to tell you what it is. You can work it out on your own if you like. But in other words, we're going to continue summing up these terms forever. And what does that sum up to? Well, it turns out that you see that this sums to 1. The remainder of this going on forever up to infinity also sums to 1. So what is this sum? This sum itself is 2 in the limit as I goes to infinity. Okay, so what do we have? We have this is less than or equal to n over 2 times 2, which is equal to n. Okay, and that gives us, in other words, big O of n. Okay, so that gives us our runtime. That's our complete analysis. And again, you can work out on your own that this summation, that the terms go to 0, that's fairly clear, and what this summation in the infinite limit goes to. Okay, and that's what we're saying down here. Sorry, that was blocked a little bit. So we have n over 2 times 2 is big O of n. Now, that's the analysis. Let's look quickly at the algorithm. That's it. This is the entire algorithm that I've highlighted right here. If you've already written bubble down, you need to start at the second lowest level. Where is that? Well, in an array, it's just at the n over 2th place. So if there are n items in your heap, then there are n over 2 is roughly the second lowest level, the rightmost point of that. And you go from that down to 0. Well, what's 0? 0 is the root of the heap, and you just call bubble down on that item. And that's it. That's the entire algorithm. And it runs faster than the naive algorithm of inserting everything one by one. All right, so we'll stop there. And I hope you enjoyed it.